Okay, so last
time I talked about.
I should maybe mute myself here.
So last time I talked about
the universal cover of a given Lie group. So let me review the definition. So suppose you have a connected Lie group G, then the universal cover of G is a simply connected Lie group with the same Lie algebra. In other words, it's a simply connected Lie group with a Lie group homomorphism from this covering group G tilde to G, such that at the Lie algebra level it's isomorphic. It's the same thing as saying that G tilde is simply connected and has the same Lie algebra as G, is isomorphic Lie algebra to G, because then this isomorphism of the Lie algebras will extend to a Lie group homomorphism from G tilde to G. We know that for simply connected Lie groups as the domain, you can always lift an isomorphism. Okay? And we looked at a whole bunch of examples of simply connected Lie groups. All right, if I can get my screen working properly. In particular, we saw that SL2C is simply connected, and therefore it's a universal cover of itself. But SL2R is not simply connected. We saw that by using polar decomposition that it is not simply connected. And our goal today is to show that, like, to describe the universal cover of this Lie group. But we will first show that, in fact, this universal cover is not a matrix Lie group. Okay? So I more or less explained the argument last time, but I'd like to go over this in more detail today. So here's the first lemma. The lemma is that if you have, so lemma is that if you have some phi underline from the Lie algebra SL2R to the Lie algebra SLNC, a Lie algebra homomorphism, so then phi underline lifts to a Lie group homomorphism. Maybe I should write it like more precisely what I mean. So then there exists a Lie group homomorphism capital phi, I don't know, I mean, maybe just phi. Well, the underline is representing the derivative. So this capital phi goes from the group SL2R into the group GLNC. All right, I think I did not choose very good notation. Maybe I should choose underline without underline here, so that phi be a Lie algebra homomorphism, then there exists a Lie group homomorphism phi, capital phi, such that its derivative, which is phi underline, is phi. So in other words, this little phi lifts to a Lie group homomorphism from SL2R into GLNC. Okay, so what is the argument? So the argument is related to the fact that even though SL2R is not simply connected, but we saw that SL2C is simply connected. And therefore, we can lift any Lie algebra homomorphism from SL2C to a Lie group level. Yeah. But now we can use this trick, which is first, we extend by linearity, we extend phi to a C-linear Lie algebra homomorphism. I denote it by phi sub C that goes from the Lie algebra SL2C into the same thing as the domain as before, which is GLNC. How is this happening? Well, phi c of x plus iy is defined to be phi x plus I phi y, for x and y in SL2R. So here in SL2C, I have this, coming like, what's the relation between SL2R and SL2C? The Lie algebras, this SL2R, SL2C is SL2R plus I times SL2R. So there's really like, you have to add the imaginaries. But on the right side, you already can multiply by I because GLNC is like Lie algebra over C. It's a complex Lie algebra. So you don't need to add anything anymore. And everything is well defined. So we get the Lie algebra homomorphism. Okay. And now, since SL2C is simply connected, there exists capital phi C going from SL2C to GLNC. Scroll a bit to the side. Such that when you differentiate it, you get this phi sub C. Okay? But now you can restrict this capital phi C to this subgroup SL2R. So now the restriction of phi sub C to SL2R is clearly equal to phi, because phi is just phi C restricted to the Lie algebra SL2R. So it's phi. Okay, so this proves the assertion. Any questions? So the trick was to use simply connectedness of SL2C. SL2R was not simply connected, SL2C is simply connected. All right, so we proved this assertion that any Lie group homomorphism from SL2R into GLN, any Lie algebra homomorphism from SL2R into GLNC leads to a Lie group homomorphism. All right, so now let's see what happens if we assume there's a covering. So the proposition is that the group SL2R, this Lie group, maybe I should say the Lie group, doesn't matter. The Lie group does not have a matrix universal cover. There is no matrix Lie group, which is the universal cover of this guy. This is what we want to show. All right, so how does the proof go? First, like, suppose such a thing exists. Okay, so the proof is that suppose that G tilde psi is the universal cover of SL2R. And so psi goes from G tilde to SL2R is the covering map. Maybe I should say where. This is the covering map. And also suppose that G tilde is linear. So this means that G tilde is contained in GLNC as a subgroup, as a closed subgroup. Okay, so now we have this map psi underlined. It goes from the Lie algebra of G tilde, which I denote by G tilde. So G tilde is the Lie algebra of G tilde. So it goes from here to SL2C. So this is an isomorphism by the definition of covering. And this means that we have a Lie algebra homomorphism, a Lie algebra, I would call it embedding from SL to R to GLNC. How does it go? This goes through G tilde. So we know that capital G tilde is a Lie subgroup of GLNC. So its Lie algebra is a subalgebra of the Lie algebra GLNC. And therefore, this map psi inverse factors, I mean, this map psi inverse composed with this embedding gives you another like embedding of SL2R into GLNC. This is isomorphism. This is injection. So this map is an injection. And I would like to denote this as still by psi inverse with a small abuse of notation. Okay. And now, by the previous lemma, we know that we can lift this psi inverse to some Lie group homomorphism. So by the previous lemma, there exists. I will just use this notation, capital psi inverse, going from SL to R to. Okay, maybe shouldn't I? Okay, okay. Let's just keep this notation. All right. The Lie group homomorphism like this. Such that its derived map, when you differentiate it and get the Lie algebra map, you get this little psi inverse. Okay. I don't know. Maybe is it confusing? Maybe I just changed my notation here. I call this lambda for the embedding. Lambda is just this composition. And therefore, here I can now change my notation, not use the inverse. I can use capital lambda. And the condition here would be that capital lambda underlined will be little lambda. Okay. Yeah, here I don't need an underline. Okay, so now what's the consequence of this? Well, I would like to claim that in fact, lambda is an isomorphism between SL2R and G tilde. So this is the claim. Lambda is an isomorphism. SL2R and G tilde. So first thing to check that the image of lambda lies inside G tilde. So lambda of SL2R is contained in G tilde. Why is that so? Well, that's because, this is the capital lambda. Well, how can we argue this? Well, we can look at the Lie algebra, relation to the lambda to the Lie algebra. So for X, in the Lie algebra SL2R, lambda of e to the x is e to the lambda underline x, which means e to the lambda x. But lambda x is in the Lie algebra of G tilde. Now, by the definition of the Lie algebra was like the vector such that e to the t times those vectors would lie in the Lie group, right? So this means that lambda, like e to the lambda x, should be in G tilde. So I have proved that any exponential in SL2R has the property that under lambda it maps into G tilde. But now this means that every element of SL2R does so, because every element is a product of exponentials. So since every element of SL2R is equal to the product of exponentials, I write this product as like e to the x1, e to the xk, x1 and xk in the Lie algebra. From this argument, on the right-hand side, we get e to the lambdas, which are all in capital, like in G tilde, therefore their products will lie in G tilde. Okay? All is good so far? So I just proved that the image lies in
G tilde.
the G tilde.
Now
I have a Lie group homomorphism,
lambda, and then another Lie group homomorphism, which was this covering map, which is this psi.
Right? Now, what is the relation between these two? So, so remember that this lambda came from the inverse of psi. Okay, so this means that if I compose lambda with psi in either way, I should get the identity map. Okay, so since lambda is just psi inverse, we have lambda of psi is the identity of G tilde, and I mean G tilde the Lie algebra, sorry. And psi O lambda is the identity of SL2R. Okay, so now these two are Lie algebra homomorphisms. What do they correspond to? So they correspond to capital lambda composed with capital psi and capital psi composed with capital lambda. So lambda of psi underline is lambda underline of psi underline, which is lambda of psi. So this is the identity of G tilde. And this means that lambda of psi should be the identity of G tilde. Because the lift of a Lie algebra homomorphism to a Lie group homomorphism is unique. And now the lift of identity is identity. So this lift cannot be anything other than identity. Identity is a lift anyway. Okay. And similarly, I think here psi should be capital. Sorry, this is capital psi. And similarly, capital psi composed with lambda is the identity of SL2R. And this proves this assertion that, okay, that, I didn't write it here, but maybe I should have written here. So now the next claim is that SL2R is isomorphic to G tilde. Okay, so we just proved that psi and lambda, the capital psi and capital lambda provide the isomorphisms of these two Lie groups. Okay? All is good? Everybody following? But what is the contradiction now? Can we have this? Can G tilde and SL2R be isomorphic from our assumptions? Why not?
Because SL2R is not simply connected.
That's right. So we're assuming G tilde is simply connected. So since G tilde is simply connected by assumption, and SL2R is not, This is a contradiction. Okay. Everybody happy so far? So we just proved that if a universal cover for SL2R exists, it cannot be linearly grouped. It cannot be a matrixly grouped. Okay, so then what is it? Then how do we construct this Lie group? Somehow the idea is clear. So what was SL2R? SL2R with this polar decomposition, it had this circle in it. It was a circle times some vector space. Remember from last time, I talked about this polar decomposition for SL2R. Yeah, here. And so basically, in order to get a simply connected cover, we have to unwind this circle inside SL2R. Somehow we have to construct a Lie group which has this property that the circle that was in SL2R, which was these rotation matrices, which you can see here, this SO2R, this is unwound. This is like opened up into a real line. Okay, but how do we do this? Okay. So the next thing I want to tell you is how one can do this. All right. So the idea is a general technique to construct a covering space for spaces that map to circle. And then I can then specialize to the case of a of the FSL2R. Okay, so let's mention what we're going to do next. So we're constructing I will just write SL2R tilde, the universal covering of SL2R. And as I mentioned, this group is important in physics, and in number theory also, and in a variety of different things. This is an important group. So let's just start with this simple and general lemma, which applies to any topological space in some sense. Okay, so let X be a topological space if you don't like an abstract topological setting, you could just say, okay, just some subset of some Rn with the induced topology. Okay, and let phi from X to S1. S1 is the circle, the unit circle, which is like a the group of 1 by 1 unitary matrices. I mean, in many ways, it's a Lie group, right? Okay, and let phi be just a continuous map. Okay, and now you form this Cartesian product and consider the following subset, which is closed. The following closed subset of X cross R, this Cartesian product, okay, with the usual topology, product topology, you know. If X is in Rn, then you could say X cross R is really in Rn plus 1 with the induced topology. It's the same thing. All right? And it's defined by, so this subset is defined to be X tilde, which is the set of points which are pairs of X and theta with X and X, theta in R, and the phi X equals e to the I theta. Remember, the values of phi are on the circle. E to the I theta is also a point on the circle. So this is in some sense unwinding X, creating some space X tilde and unwinding it. All right? Unwinding, which unwinds X. Okay? So then So the natural map. So we have this natural projection map that goes from x tilde to x. What does it do? Where does it take as a point x theta on this x tilde? What, like, there's only one thing it can do. You can tell me what it does. What is this P? You should define it for me. Yeah? Just x, exactly. That's the only thing you can get a point x from this in the suburb. No, without extra information. Okay. So this projection map P is what we call a covering map. And I'll explain what this means. So this means, this word covering map here means that for every point in X, there exists some open set containing X, open set in X, containing this little X. Maybe I should write it below. Okay, maybe I should write it like this. Such that when you look at the inverse image, under P of the set, you get several copies, several disjoint copies of U. So this means infinitely many disjoint copies of U. Let me give you an example before I prove this assertion. Okay, so what is the example? Let's take X to be the real line, and this phi from R to S1, phi of theta is just e to the I theta. This is an example of a map from X to S1, right? Okay, so now what we want to do is we want to consider the set of points in R2. So how does it look like? So X tilde is in R2. And how does it look like? Maybe I just draw another axis. I'm not sure if I'm doing this right. Okay. So what is X tilde? It's the set of points of the form X theta, such that phi X equals e to the I theta, but phi X is just e to the IX. Okay. And so this means that I'm considering, so what does this mean? This means that X is theta plus 2 pi k for some k, for some integer k. All right. Which means that for any, say, I mean, if this is the x-axis and this is the theta axis, this means that I'm, for any x, I am basically considering these parallel lines. I mean, for any x, I should have like x plus 2 pi k. So I'm basically considering such lines. Okay. And now if I look at the projection will be just the projection of all these lines to the first component. Any point will project to its x-axis component. Okay. And now if I take some interval here, or maybe I should maybe choose it here. Maybe it's better. then what are the inverse images under this map P? So P is this map along this dotted line. It's like vertical projection, and the inverse images will be these line segments. Okay? So the inverse images are under this P, they're homeomorphic to the image, right? This image is this interval, and the inverse images are these disjoint green intervals. Okay? So that's what this assertion means. Okay? Now, why is this true? Why is this lemma true? So, okay, is this clear? Is this clear? Maybe I should just keep the statement of the lemma for a moment. So you can stare at it for a while, and if you have any questions, you can ask me. So the main thing is that, so what the, like maybe more sort of in the more sort of abstract picture. So we have here this X, and here we have this X tilde, and we have this map P. And the claim is that the property of the P is the following, that for any point little x, there is some neighborhood U, which I show by this hashed disk, such that its inverse image is a disjoint union of disks, such that the disks are homeomorphic via P to their image. So the P restricted to each green disk is a homeomorphism. It's a continuous map with a continuous inverse. Okay? It's a bijection which is continuous with a continuous inverse. Okay, so now let's prove this. So the first step, so the key idea is the following. The key idea really is this map, and maybe I should draw this picture. So we have this space X, and we have the circle here. And we have this real line. And we also have this map that takes any t to e to the it. This map that I had for like phi in the case of x being the circle, x being the real line, okay? Where is this map phi that we're talking about? This map phi, it's a map like here. The goal is to lift this map to the map phi tilde into R. But we cannot do this for the entire set X. For example, when you think about this map, well, this is a special example. But anyway, if I had a circle here, if X was a circle, I couldn't get a map from the circle to the line that projects after composition to the identity map on the circle. Okay? But at least I am able to do this on small open sets in this set. So the first step, and that is the key to define. That is the key to show that P has this property. So here's the thing. So let U subset of X be open such that we can lift the restriction of phi to U as a map from U to S1 to a map phi tilde from U to R. And this means that P of phi tilde equals phi. So suppose, well, not on X, but maybe on some small set, some open subset U of X, we can find a map from U to R such that when you project down via this exponential, maybe I should write this more precisely because we had a P another like place. So this means that e to the I phi tilde X equals phi x for x in U. Okay? Which means if you go down this diagram after phi tilde, you get phi, but only on the set U, not on all of x. We can't hope that in general we can do this on all of x, okay? So then, P inverse of U is homeomorphic to infinitely many copies of U, disjoint copies. Okay? So why is that so? That's because, so let's see which points satisfy this condition. Okay? So suppose x theta is in the inverse image of U. So this means that P x theta is in U, but on the other hand, this condition, what does it mean for x theta to be in x tilde? Okay, so x theta in x tilde also means that phi x is e to the I theta. All right. Right. So let me see. Did I describe it correctly? So x theta is in P inverse U, and but on the other hand, we have this phi tilde. Okay. So this is equal to e to the I times phi tilde x. All right. That's because of the condition, the relation between the two guys. Okay. Okay, so now what this means is that theta minus phi tilde x is in 2 pi z, which means in this set, like 0 plus minus 2 pi plus minus 4 pi plus minus 6 pi, so on, okay? Because the exponential e to the I theta equals e to the I, like, I mean, if e to the I alpha equals e to the I beta, this means that alpha minus beta is like 2 pi k for k in z, okay? So this is what I'm using here, right? So now, so now you could say that you could now basically like sort of divide the x thetas in the inverse image based on the value of this difference, okay? So now we can set, UK to be the set of points x theta such that P x theta is in U, and theta minus phi tilde x is K. The K for any K in Z. Okay. And so now the point is that, in fact, the UKs are obtained by translation from each other. So if x theta belongs to UK, then x theta plus m also belongs to UK plus m for any n. That's because if you apply the projection only sees the first component. And at the same time, phi tilde of x equals e to the I times theta plus m. Theta plus 2, maybe I'm missing a 2 pi. Wait, here I'm missing a 2 pi here, right? Here I'm missing like 2 pi. Here also I'm missing a 2 pi, okay. So this difference, as I mentioned, is like a 2 pi times k. So it's like divided by 2 pi. Maybe I should write divided by 2 pi. It's k, okay? And this is x plus 2 pi m. Yeah, here, okay. X comma theta plus 2 pi m is in uk plus m. So these UKs are in fact obtained by translation from each other, right? So the translation would be by like units of 2 pi m. So from UK to UK plus m, you should translate the points in the theta direction on x tilde by this 2 pi m, okay? Therefore, a similar situation occurs here. So this like these sort of layers on top occurs also in x. Each of the UMs, it's homeomorphic to you, okay? And now, okay, so now we know that now we have shown that if u is small enough such that you can lift this map, you have this. But I never said that u is for small enough you can lift phi to phi tilde. Let me explain why that happened, okay? The second step is that any point has a neighborhood for which that lift exists. So the second step is that take any point in x, then there exists an open set, an open neighborhood u of x such that phi restricted to u lifts to a map phi tilde from u to r. So how does this work? Well, let's look at the picture. I will explain the argument by the picture. So here we have x, and here is this little point x here, and here is the circle. And this map phi maps this point x to phi x some point on the circle. Now, because of continuity, you can take some arc that skips at least one point on the circle, and then the inverse image of that arc, well, you can take an open arc, and the inverse image of that arc will be some open set. In other words, you can take some open set such that its image lies in a proper arc on the circle, an arc that misses one point, like a small arc near this point, okay? So now, if you look at this map, this projection, this sort of exponential map, remember, I wanted to lift this phi to some phi tilde into the real line, okay? So that the picture of maps commutes. So this is R. So now what is the inverse image of this arc? The inverse image of this arc will be some disjoint line segment. And that's because you have skipped at least one point on the arc. Intervals of length 2 pi are mapped to the whole circle. But if you remove integers, you will be mapped to points of the circle, say, except the identity, and so on, okay? So now, well, each of these intervals, this exponential map, t to e to the it, is a homeomorphism from each of these intervals to this arc. They are really the same thing. This exponential on this line segment becomes a bijective continuous map with a continuous inverse onto the arc. Okay. And therefore, well, because the two things are really homeomorphic, you can compose with the inverse and get this map from U to this arc. to the line segment. Sorry, to the line segment. So all you need to do is to pick some point, say x tilde here, such that, well, or maybe I should call it theta tilde. Not even tilde. I don't even need a tilde. Like maybe I just theta, such that e to the I theta equals phi of x. And then I can just identify this arc with this line segment and then compose the inverse map to get this map phi tilde, so that if you compose back, you get phi. Okay. All right. So now with these two steps, we have the sort of property of this map that we were looking for. That the inverse image of some small disk is just this disjoint, infinitely many disjoint disks above. Okay. So now you can do this construction. Basically, this is the trick to construct the covering space for SL2R, but this also works for any space. However, as you see, it doesn't always provide a connected space. In the case of the real line, it provided something disconnected. This was like disjoint line segments. Not surprisingly, because the real line is really the, it's as a Lie group, it's simply connected. It cannot have any non-trivial covering. So this construction should not generate a new covering, like a proper covering, okay? A proper universal cover, so to speak. All right, but now let's see how this works for the case of SL2R, okay? So let's now look again at SL2R explicitly. So now we use this construction. So what is this construction? So okay, how do we do this? So what is SL2R again? So SL2R is the set of 2 by 2 matrices, A, B, C, D, with AD minus BC equal to 1, A, B, C, D, and R. Now I have to give you this map phi. Remember, I should get a map from X to S1, right? So what is this map phi? So what is phi of a matrix? A, B, C, D. It is going to be the following quantity, which might look a little bit strange, but I can explain where this comes from. So we define this number. Ci plus D divided by the absolute value of Ci plus D. So C and D are real, so Ci plus D is a non-zero complex number. I is the square root of -1, and therefore when you divide it by its norm, you get a unit complex number. It's on the unit circle. Okay. All right. Any questions about it so far? And so therefore, this G tilde that we construct is the set of pairs G theta, where G is in SL2R, and theta is in R, and well, phi G as defined above is e to the I theta. So it is contained in SL2R cross R. Okay, so it's something in something bigger, of like a bigger dimension. But I mean, we're killing one dimension because we have this identification. We have this extra condition. All right, and I want to show that in fact, this set is a Lie group, and then the projection map. So we have the projection. From G tilde to G being SL2R, right? This was the projection mapping X theta to X, right? And I want to give a Lie group structure here on G tilde so that this map becomes a Lie group homomorphism. Okay? Note that this Lie group structure is not the group structure of the Cartesian product of these two restricted, because that as a subset will not be a subgroup. Okay, so it's something more interesting than that, which I'm going to explain. So are there any questions so far? Okay, so the next thing I want to show is actually this G tilde. Before giving the group structure, we have to make sure that something degenerate like this example doesn't occur. In this example, when I did this construction, X tilde was disconnected. It was these lines. But I want to show that in the case of SL2R, contrary to that intuition, something else happens. In fact, you get a connected and path connected space. All right. So the first proposition is the following. So G tilde is connected and path connected. Actually, well, in addition to that, maybe I should say, well, okay. All right, connected means path connected. I'm sorry, I'm not saying this correctly. So it's connected meaning path connected and simply connected. In other words, all the loops can be shrunk. So first, let's make sure that we actually got the right space. Forget about group structure. Why did we get the right space? So the proof of this has to do with the following other sort of decomposition for classical groups, in particular SL2R. Okay, so you've seen the polar decomposition. Here I'm going to talk about slightly different decomposition. I will not talk about it in general, but just in the case of SL2R, but in fact, it extends to all the groups for which we did the polar decomposition. Okay. So we have this decomposition. We can describe SL2R as the product as a spaces, not as Lie groups. Maybe I just say as topological spaces, or like like a manifolds, I would say. Where B is the set of all matrices of the form T S0 1 over T where T is non-zero and S is any number. This is the subgroup. B is a subgroup of SL2R. And not so surprisingly, S1 is just the SO2, which is cosine T minus sine T, cosine T T in R. Okay, the circle subgroup. So I want to describe a way of decomposing SL2R as a Cartesian product. To do so, I explain how you write an element of SL2R as a product of an orthogonal matrix and a triangular matrix. So this is equivalent any G in SL2R can be written as a product of a triangular and an orthogonal matrix. Does it remind you of anything in linear algebra? The polar decomposition was something we proved using linear algebra. This one you should know. You have seen this before. What does it remind you of in linear algebra? Why is this true? This is really the Gram-Schmidt process. How many of you know the Gram-Schmidt process? Orthonormalization, Gram-Schmidt. Does anybody know here? Really? Nobody knows it? Yeah, you guys know what it is. Okay, so what is going on here? So suppose I write the matrix in SL2R by its columns. So V1 and V2 represent the columns of this matrix. Okay, what does the Gram-Schmidt process do? First, suppose you can think about V1, V2 as a basis for R2. And now first you normalize the first vector, and then you subtract a suitable linear combination of the first from the second. So here we have V1 over V1, and I do V2 minus CV1 divided by its norm. And then these two become orthonormal, right? Unit vectors that are orthogonal to each other, an orthonormal basis. Okay, so this is the matrix which is of this form, basically. Okay, it's so therefore you have to say what we did to the matrix G to get it to this form. Well, the first thing you did was a scaling of a column. Scaling of a column means multiplying on the right by some diagonal matrix, right? Yeah, so if you multiply G by the matrix C1, then you get like CV1, V2, right? Okay, it's like multiplying by diagonal matrix, okay? And this operation you can also describe by multiplying on the right by some triangular matrix. Okay? So the product of diagonal and triangular, so maybe I should say this is done by multiplying on the right by some diagonal guy, and here by some triangular guy. And now the composition of these two operations is like a product of two matrices. They're both triangular. One is diagonal, also triangular. So the product remains triangular. So this means, this means that I multiplied G by some other matrix B, which is triangular. And I got some matrix K, which is in SO2R, which is this S1. Okay, so this means that G is K times B inverse. But the inverse of a triangular matrix is triangular. So this guy is orthogonal. This is in SO2R. In fact, it's a special orthogonal, but that doesn't really matter here. And this guy is triangular. So this whole assertion about this decomposition was really linear algebra. This was Gram-Schmidt. Thought about like in a slightly differently, construed it slightly differently. Gram-Schmidt in disguise. Okay, all is good? Did you understand what I said? Any questions? So any matrix, even like in SLNR, you can write it as a product of a triangular matrix and an orthogonal matrix. And that's just because of Gram-Schmidt orthonormalization process. Okay, so now back to this. We wanted to prove that G tilde is connected and simply connected. Now let's see what this means in the context of like constructing this G tilde. So what is G tilde? So G tilde is a subset of G cross R. Okay, but what is G cross R? G cross R, as we just saw, it is really B cross S1, triangular matrices cross S1. By the way, you can also see that the triangular matrices topologically, this is R star cross R, because you have these two parameters, S and T. S is in like R star, like T is in R star, S is in R. So you could see that you actually have some homeomorphism between these two. It's not so difficult to show together like a bijection, continuous bijection with a continuous inverse. Okay. But anyway, that's not so important. What's important is that I can write this as B cross S1 cross R. Okay. And now, what is G tilde? So G tilde, oops, G tilde, if I can manage to write. Is the set of points of the form B times Z times theta, where B is in B, and this Z guy is in SO2R. So it's really S1. So I can represent it by the same complex number. And the theta is in R. And we also know that e to the I theta equals Z. Right? That was the condition. So now this can be written as B, but Z is e to the I theta, right? So this is e to the I theta. Theta, where theta is in R and B is in B. But now you see that this parameter suddenly becomes irrelevant here. This depends on theta only. So this you could just project to the first and the third component, and that projection will be homeomorphism because the second component has no freedom. So this is homeomorphic to what you get as a projection to the first and the last component. Maybe I should write it as like a B thetas, where B is in B and theta is in R. But what is this last space topologically? The last thing is just B cross R. And as I said, B is just R star cross R. So you get really this space. You can see that this is connected. This is really R3 minus a plane. Okay, you just removed points with X coordinate 0. That is just the YZ plane. You removed R3. You removed one plane from R3. Wait, did it make it disconnected? Well, I shouldn't say R star. Sorry, I think I should say R plus. Did I say R star? Yeah, I think I made a mistake here. So this is not R star. This is actually R plus. You don't, you can pass the negative. So if you want to take a -1 here, you could look at the matrix 0, -1, 0, 0, -1, but that's already in SO2 for theta equals 0. For theta equals pi. Okay, so you could say that like this is like for theta positive. So I'm sorry, it was not correct. So this is R star is like disconnected for sure. Like remove 1 point from R is disconnected. Okay, so you have R plus, and finally you also have R plus. Did I make this mistake anywhere else throughout? Okay. Okay, so like a product of connected spaces. And they're simply connected. In fact, you could say R plus and R are homeomorphic, just using the exponential and log. You could say this is really the homeomorphic to R3 as well. Okay, so this proves that G tilde is really as like topologically, this is just like R3. So it's connected and simply connected. Okay. Okay, so at least topologically we got what we wanted, but now what is the group structure on this G tilde? Okay, so the group structure is rather complicated, and it's actually very interesting. And it is connected to many different things, to modular forms, number theory, to like Hecke operators and many different things. So how do we define this group structure? So let's come back to this group, G tilde. Let me or rather G, just show you what G is. So G is this SL2R. And now I want to introduce another ingredient in this picture, which might surprise you, the hyperbolic plane. How many of you have heard about the hyperbolic plane? Nobody? Nobody knows what it is, the hyperbolic plane? What is the hyperbolic plane? So you can think about this as the set of complex numbers with non-zero with positive imaginary parts. Okay, so like geometrically, you could just draw this. Maybe I should draw the y-axis as well. Okay. Excluding the x-axis. Okay, this is h. All is good? All right. So now I want to define transformations coming from SL2R on the hyperbolic plane. So given G in SL2R of the form A, B, C, D. So we define J depending on G and a complex parameter Z to be CZ plus D. Okay, just as simple as that. It's not like what you saw as like this function phi before. Okay. So now note that JG defines a function on the hyperbolic plane. In other words, maps points with positive imaginary part to points with positive imaginary part. Let's check that. So if you take Z equals x plus iy, then what is JGZ? This is like a CZ plus D. And to see the imaginary part of this, well, it's really just to expand, right? So you just write C times x plus iy. Did I write it correctly? Ah, okay. I didn't really write it correctly. Okay, so maybe here. Okay. This is not correct. Okay. So okay, so here's okay, there's something. Okay, I missed something in between. Sorry about that. Okay. So here's a remark first. Okay, so maybe here's a remark. So G itself defines a map from H to H given by the G of Z. Maybe I should call it like phi G of Z. I'll just write it as G of Z. Hopefully it's not confusing. As AZ plus B over CZ plus D. Okay, for Z in H. So now I want to show that in fact, first of all, the denominator doesn't vanish. And in fact, you get a map from H to H. How many of you knew this fact? Nobody? You knew this fact? What are these functions called? Mobius transformations. Okay, now let's check this. So let's check this. That in fact, points with positive imaginary part are mapped to points with positive imaginary part. So I write like A times X plus IY. I mean, maybe first I should get rid of the denominator. So AZ plus B over CZ plus D is AZ plus B CZ bar plus D divided by CZ plus D squared. I just multiplied by the conjugate of the denominator to get rid of this denominator. Now the denominator becomes a positive number. Note that C and D are real, so I don't need to conjugate them. And now when I expand this, what I get is like AC absolute value of Z squared plus BD, which is the real part, plus AD Z plus BC Z bar, which is, well, if I write Z as X plus IY, then I get AC Z squared plus BD plus AD plus BCX plus I times AD minus BCY. Okay, so remember that Z is X plus IY. So Z bar is X minus IY. I made the substitution and I simplified and I got this. And now what I see is that this is 1 because I got something in SL2R. It's the determinant. And this is positive. So the product of, I mean, this is just again Y. Right? Yeah, but I mean, but the thing is that I also have to divide by some number. So I mean, it is not true that these transformations preserve the imaginary part, but I mean, the numerator does, but the denominator is like a positive number. Okay, so I mean, I forgot the denominator. Sorry. Okay, so like a CZ plus D squared. Like a CZ plus D squared. Anyway, you see that the positivity of the imaginary part is not affected, right? Because the imaginary part is this divided by this. Okay. Okay. How much time we have? Okay, so we didn't finish this, so I will just say one more thing about this J. All right. So we had this J, which was just the denominator, CZ plus D, and we also have these Mobius transformations. In what context do you know about Mobius transformations? Justin? Huh?
Complex analysis.
And what did you do with them?
Great question.
You know, Mobius transformations provide conformal maps, say, between various domains. Like if you want to show that like a disk and the upper half plane are like conformally the same, then you can use Mobius transformations, so combinations of these things. Okay. Maybe the last thing I say is that is this relation that J. Now here's the important relation. J, G1, G2, Z is J of G1, G2 of Z, J of G2 of Z. Almost like a group homomorphism, but not exactly. There is some twist. All right, so this is for G1 and G2 in SL2R and Z in H. Note that by what I just showed, G2Z will also be in H, so this makes sense. Okay? And now we are going to use this to define a group operation on this G tilde and show that the group operation, like the projection map, becomes a group homomorphism. I guess we can stop now, and this will be the continuation, which I will do next time. And next time I'll also talk about analytic Lie groups, and which is a little bit more from the textbook.